All right, survivors. How are you? Good, good. Well, yeah, I mean, half joke and half truth. You survived through all the difficult part of the course. And then today we're going to be talking about this thing called the physics-aware recurrent convolution. And then this is going to be the last kind of technical topic. And then tomorrow and then the day after tomorrow, we're going to be looking at some examples and, it's going to be a little more relaxing. And then that's going to be the end of, end of the course. Time flies. So since you guys survived through, hey, more survivors. All right. So since you guys survived through the, this up to this point, to talk a little bit more about the quiz, there are 25 questions, all very difficult. True or false, very difficult, 50-50. I think mostly it's going to be about the basics of deep learning. And then there's, I don't know, half of the question roughly, give or take, about pin, neural operator, and then this thing. Okay, so up to today's, lecture is going to be the scope of the quiz. So hopefully you will find, like I said, it's not terribly difficult, but still. All right, so we've learned a lot of different things. And as a matter of fact, I mean, I'm proud of you guys to, to survive here because it's a lot of topic that was kind of condensed into, only 2 week of, course. So this is something I would have offered as a 1 semester, course with deep learning as a separate, prerequisite, right? But there are so many things to cover, and then we kind of condense everything into, 10 days of lecture. But despite that, you guys done a phenomenal job. So, so that's great. So, among the things that we, discussed so far, is this concept of physics-informed loss and the physics-informed neural network. And then also yesterday we talked about the neural operators. Now we're going to be viewing this from a slightly different angle. Okay, so we talked about the mathematical definition of the physics-informed loss, and then we talked about the the actual implementation of physics-informed loss and the neural operators. But we're going to be viewing this, from a slightly different perspective, which is the perspective of differential geometry. Obviously, we're not going to go into the real hardcore differential geometry because this is, kind of a mathematics graduate level. But we're going to be, viewing this problem of learning physics from a geometric perspective so that you have a better, visual of what's happening in the world of paddle. So the physics-informed loss, instead of talking about this abstract, generic example, let's consider more specific example of the heat equation, right? So heat equation looks like this, where the partial derivative, the time derivative of u equals to some coefficient alpha multiplied by the Laplacian of u. And what this entails is basically kind of a surface where you have the initial condition. So we have the r-axis. R-axis is the material axis. So this is the physical domain. And then we have the time axis. And what happens is this curve sort of evolve over time so that after certain time delta t, this is what you're going to get. After time delta t again, this is what you're going to get, and so on and so forth. And eventually, if for some continuous time t, this is going to be basically a surface that looks like this, right? So this is something that we saw already. And then the idea of physics-informed loss or physics-informed neural network was essentially to do the surface fitting, okay? So a neural network with TNR as the input that spits out U as an output was our parametric model to describe the surface. So the equation of that surface was actually what was modeled by an artificial neural network, right? So that was kind of the idea. And then what is defined as a data loss is basically the difference between the ground truth and then the surface. So if you have a snapshot, for example, of the evolving temperature, right? That snapshot is going to be a curve that looks like this, right? And then on that curve, we know the ground truth. So what we would like to do is to, pinch the surface and then lift it up so that the surface gets closer to the ground truth, right? Of course, this is for the purpose of illustration. So the ground truth doesn't necessarily have to be a curve. It can be some scattered point somewhere. And then we saw that the ground truth is usually, sampled at the initial condition, time t equals to 0, as well as the boundary. But without loss of generality, right? The ground truth is basically some target points. And then we're kind of pinch, and lifting up the surface to move the surface closer to the ground truth is kind of the idea of data loss. So far, so good? So that was the visual that I wanted to introduce. Another thing is that the idea of physics-informed loss was basically defining the curvature, sorry, not the curvature, but the slope of the surface, okay, based off of the governing equation. So we sample points called the collocation points. And at each collocation point, what do we evaluate? We evaluate the time derivative, which is the slope of the surface in the direction of the t-axis, right? And then the Laplacian of u, which is the second order derivative in the r-axis, right? And then, first order derivative is a slope. The second order derivative is the rate of change of the slope, which means the curvature. So if a surface is flat, then slope doesn't change, it's flat. And therefore the curvature is going to be 0. The rate of change of slope is going to be 0, right? But if the surface is curved, then the rate of change of slope is going to be some value. And basically what we're saying is, okay, the curvature along the r direction should be the same as the slope in the t direction. Okay, so that's really the geometric meaning of the heat equation. So here we have the blue arrow pointing down. Okay, that's the curvature, okay, of u evaluated in the r direction. Okay, so that's why, by the way, the heat equation diffuses any, any spike of value. So when you have a value that is, not flat, right? When you have a, imbalanced distribution of a temperature value, then the diffusion equation is going to suppress that, spike, right? And then eventually make it flat. And that's because whenever you have a positive curvature or negative, the non-zero curvature, right? That is going to induce the time derivative in the t direction. So graphically speaking, geometrically speaking, the spatial derivative part is the blue arrow pointing down. And then we're basically saying that, hey, we want, that blue arrow to be the same as the time derivative, which is the red arrow. And then, of course, in this illustration, I consider some large time delta t, but, if we consider a small time delta t, right, then by equating the blue arrow with the red arrow, right, we can describe the dynamics. So that's, the geometric meaning of the heat equation. Does that make sense? So intuitively speaking, if the data loss was picking a surface and then lifting up, right, to move the surface closer to the target point, this physics informed loss is what makes the surface smoother. Okay, so like I have this tablecloth, and then let's say I'm lifting this up. The surface is going to look have wrinkles and kind of wriggly. But then what the physics informed loss does is to smooth out the surface so that it looks nice and flat and smooth. And then the benefit of having a smooth surface is that it generalizes better, right? So we spread out an arbitrary number of collocation points, and for each of the collocation point, we're ironing the surface to make the surface smoother. Okay, smoother in the sense of following this relationship. Okay, now, so physics informed law, physics informed neural network was nothing more than those two processes where we're fitting the surface and then smoothing out the surface. So that's what I just said. Now, on the other hand, the neural operator approach, we have a slightly different visual. Okay, so we talked about the Banach space yesterday. The Banach space is a space of functions. And in case of neural operator, instead of focusing on one particular physics phenomena corresponding to specific boundary condition, initial condition, and the physics parameter, we're considering more larger variety of physics phenomena with varying initial condition and varying varying initial conditions and boundary conditions and physics parameters. So in this setup, a point in this Banach space, okay, is a function representing the current state of the system. So in case of a heat equation, that entire curve, okay, a section of that surface is represented as a point. Or in the case of fluid dynamics, one configuration at one time t, one configuration of fluid is what corresponds to a point in the Banach space. And with that being said, what we call the dynamics is, so with that being said, we basically have a space of all possible configurations. Okay, where if we pick a point over here, that point may correspond to this configuration over here. If you pick a point over there, then it may look like this configuration over there. So all possible fluid configurations, okay, all mathematically possible. Doesn't have to be physically possible, but all mathematically possible configurations of the system, okay, will be what's covered by this Banach space U. So what we call the dynamics, okay, is a particular trajectory in the space of U. Because a point corresponds to a fluid, a configuration of a system, the trajectory is going to be a continuous change configuration. So if this is U0, then the other points on the trajectory may represent the evolution of this physical quantity over time. So that we start from here, and then after time delta t, the configuration changes to this. And then after time delta t, we have this snapshot over there. And then after delta t, we have this snapshot over there, and so on and so forth. So we're kind of lifting up our view from very, very narrow view of one particular trajectory to the space of all possible, trajectories depending on different initial conditions, depending on different physical parameters. So if the initial condition change, then you will start from somewhere else and then flow, right? If the physical parameter change, such as the Reynolds number or the fluid density or anything like that changes, you will still start with the same initial condition, but the overall trajectory may look totally different, right? So that's kind of the situation that we're considering over here. Now, the idea of neural operator, okay, introduces another mathematical object called operators, okay? And the operator is a mapping from U to itself. So in fancy terms, if you want to impress somebody, this is called an automorphism. Automorphism means mapping from itself to itself, okay? So it's a mapping from U to U itself. And what this, operator does is to take a point as an input and then spit out another point in the space of U as an output. So here we have the identity operator, E. The identity operator does nothing. It will take a point in the space of U and then spit out the same point as an output. So nothing really interesting going on. But let's say, a point somewhere on the operator space that is not identity. What this guy will do is to take a point at the identity, take a point U0 as an input, and then spit out another point, okay, in the space of U as an output. You can also consider another point in the operator space, and then that point is going to take the initial condition as an input, and then spit out another point as an output. And you can almost, think of a trajectory of the operator in the space of operators, okay, not in the space of U. And then along this trajectory in the operator space, what happens is for any given point, U0, it's going to spit out a point U after certain time t. And this trajectory of operator is sort of reusable in the sense that if the same trajectory of operator was able to describe the dynamics starting from the initial condition U0, then the same trajectory of operator can also describe the trajectory, the dynamics starting from V0, a different initial condition. So what happens in that case is you throw in V0, and then this operator over here will spit out a corresponding point, okay, somewhere on this trajectory. So in case of neural operator, we're interested in learning, this guy over here. And the hope is by learning this operator, you should be able to describe all possible dynamics, okay, across different initial conditions, which was exactly what we saw last time. Yesterday, right? We had this Darcy flow example where we had different, permeability as the condition, right? And then for those different conditions, without retraining the model, we were able to make predictions, right? So that's kind of the case. Yes. That's a great question. So that's actually something that's missing in this figure. So thanks for pointing that out. The physical parameter will change the trajectory of the operator. Okay. So imagine you have sort of a joystick, okay? And the joystick represents the physical parameter. And then by changing the joystick, the curve changes on the operator space. And because the curve changes, now given the same initial condition, the different operator will change a different trajectory. Operator is parameterized parameterized by time, by physical properties. Yeah. Yeah. Not space, because the operator eats a function that's defined over space. So this doesn't directly interact with the space itself. Yes, you're right. Okay. So this is a yeah, sorry. So in this, that's another great question. So in this particular scenario, collocation points are, conceptually speaking, collocation points are points inside of this point, because this point is a function that covers a space, right? So rigorously speaking, collocation points are points inside of this point, which, doesn't make sense. But, like I said earlier, this point on U essentially represent one snapshot, and collocation points are placed, right, somewhere in there. So in that view, it's hard to define collocation points very clearly, but maybe, you can consider collocation points as, sort of sub points, like those little atoms, right? Like, this dot over here looks like a dot, but if you, zoom in to the quantum level, then you get to see, like, lots of different things going on. So maybe, that's the analogy I would use. Yeah. So, this view of differential geometry is actually a very useful way of understanding partial differential equations and, defining the whole idea of learning physics. Yeah. As a matter of fact, this is kind of a, contemporary topic in the modern mathematics as well. So there are people actually, approaching the problem of PDEs, with the tools of differential geometry. So even mathematicians, they study PDEs using differential geometry. This is kind of a new, idea, even to the math community. So previously, the conventional way of handling PDEs was by using the tools like Fourier transform, and then, you could basically map the solution of PDEs to the Fourier space, and then over there you calculate. Yeah, so that's the traditional, PDE literature, and then most of the textbooks about partial differential equation, the number one thing that they will come up with is things like Fourier transform or Laplace transform, and then, you map the original function to some, Laplace space or a Fourier space, and then, do the calculation there, and that's how you find the solution. So that's the conventional way of, handling PDEs. A newer, and in my opinion, much more intuitive way of solving PDEs by using differential geometry. And we're, yeah, here giving the gist of what that theory might look like. So obviously, if you, go deeper into this theory, there's a lot more going on. And, even, some of those topics are beyond my, understanding, because like I said, this is a contemporary topic in mathematics, and mathematicians are a lot smarter than me. So, after a certain level, I don't fully grasp, especially nonlinear PDEs. I don't fully grasp what's going on, but at the conceptual level, this is kind of the idea. Now, the important point, the reason why I'm bringing this up is, this view allows you to rethink about the problem of physics. Okay, so the the brilliant idea of neural operators was, instead of viewing the physics learning problem as a curve fitting in the Banach space, okay, where the curve now has to be in different shape, right? So you not only have to fit the curve, but also that curve needs to be parameterized by different initial condition, and different physics parameters. So you should be able to move the curve, right, according to the initial condition. You should be able to deform the curve, according to the physical parameters. And this is a very difficult, curve fitting problem, right? You want to fit the curve, but the curve kind of changes, right? It's a very difficult curve fitting problem. Now, if you move to the operator space, you don't have to fit many curves. You just need to fit one curve, and that curve will represent everything, right? All possible scenarios of evolving dynamics can be represented by one curve. And therefore, the problem of learning neural operators is much simpler, okay, compared to the problem of learning or fitting the curve in the original Banach space. Yes. Yes. That's a great question. So I draw this more like a curved space because theoretically this is this space of operators is what's called a Lie group, and Lie group is a special type of Riemannian manifold. Manifold meaning a curved surface, and likely this is a lot more complicated than just a flat space. Whereas the Banach space, we basically consider it as a vector space. Okay, so the points, okay, essentially follow the usual properties of the vector space. So that's why we're representing that as a flat space. Whereas the space of operators is what's called the Lie group of operators. And the Lie group is actually a manifold or a curved space that has certain structures. So if you are doing any like robotics research, you probably heard the term Lie group, SO3, those kind of things. Space of operators is also a Lie group. Again, the exact definition of Lie group and those kind of things is beyond the scope of this course. But let me just say that mathematically, there's a reason to believe that the space of operators is actually curved. Well, so far, we're not introducing any assumptions about the operators. So the operators can be nonlinear. As a matter of fact, and I'm glad actually you brought up the fact that the space of operator is curved. So how do we define a straight line on this curved surface? Well, let's move away from this, but consider the example of the Earth. Okay, unless you believe that the Earth is flat, how do you define a straight line from Jabalpur to Washington, D.C.? Great circle, yes. So you define a great circle that passes through those two cities, right? And then the path that is along the great circle is probably the shortest path. So if I can afford my private jet and fly from Jabalpur to Washington, D.C., then I would take the path along the great circle, and that's the fastest route that I can get back home, right? Yeah, funny thing, on the way, actually, I realized that the trajectory from, so I made a stop at Paris, and then from Paris, I flew to Delhi. And then, if you draw the straight line, actually, on the way, there's Ukraine and Afghanistan. So actually, the plane was kind of making a detour to avoid those two places. So it took actually a couple hours longer. So that's obviously not a straight line, right? Because I took the detour. The straight line would have been, across, from Paris to Delhi, across Ukraine, and then, Afghanistan, and then, all the way to here. So that's, what is equivalent of a straight line on the curved surface. Okay. In fancy terms, it's called geodesics. Yeah. So geodesics is the straight line on a curved surface. And then anything that deviates from the geodesics is considered to be a curved line on a curved surface. Does that make sense? So what we call linear partial differential equations would look like a straight line or the geodesic on this curved surface. Okay. And what we call nonlinear PDEs will have this arbitrary shape. Does that make sense? Now, in differential geometry, the way we define, well, actually, I'm going to just stay here. The way we define a straight line on a curved surface is by using a tangent vector at point E. And then if you keep follow theory, that will produce the straight line. Similar to, you know, like let's say I'm sitting here and then the direction in terms of where Washington D.C. might be located. And then I, stand along that direction and then just keep marching forward without turning left or right. Okay. That would have been the straight line or the greatest circle from here to Washington, D.C., right? So if I keep following that vector, even though because of the curvature of the Earth, that vector sort of turns, okay? As far as the tangent space is considered, I don't make any twist. I don't make any rotation, right? And that's how I would, define a straight line over there. So the idea of learning operators, okay, the trajectory of operators, in case of linear PDEs, we don't actually have to learn the entire trajectory. You just need to learn the vector. Vector pointing the direction of Washington, D.C. I don't have to, or all the cities in between, okay, Jabalpur and Washington, D.C. I just need to find the direction, and that direction will uniquely determine the shortest path. So in case of linear PDEs, the only thing that we need to learn is the vector, not the entire set of operators. Examples of linear PDEs, almost all problems that you will encounter in real world. Heat equation is a linear PDE. Schrodinger's equation in quantum mechanics is a linear PDE. What else? The advection diffusion equation is a linear PDE. Almost everything that you ever heard of is a linear PDE, because nonlinear PDEs are kind of rare. And even if there is a nonlinear PDE, we will eventually linearize that and then consider it as a linear, dynamics. So a lot of the problems in the real world is actually a linear PDE, which means that in the space of operators, I have a straight line. So instead of learning the entire set of operators, now the question is, what if we just learn the vector, just the direction? Because once we learn that direction, then the rest is uniquely determined. Does that make sense? So that brilliant idea is what's behind, this thing called the physics aware recurrent convolution. So before we get there, that's kind of the motivation for this. Here's a graphical illustration of what PIN does and neural operator does. So obviously the PIN, we're basically solving the curve fitting problem on the Banach space U, and then we define the data loss and the PDE loss, right, or the physics informed loss over there. Whereas now with the neural operator, we introduced the operator manifold G, and then the trajectory on that operator manifold is basically what we're trying to model using neural operators, right? Now, physics aware recurrent convolutions is slightly different Okay. And like I said, the key idea is instead of learning the entire trajectory, let's learn the vector. Okay. So we'll get to that. But let me first, introduce the motivation here. So the physics-aware recurrent convolutions, or PARC, is actually the work resulted from my own team's research. So which is why I'm, explaining as if this is the best of the methods, which might be true. But we started with this problem of predicting the dynamics of what's called the energetic materials. So what you're seeing over here is basically an explosive. So we have particles over there, and then those explosive particles are kind of packed in a space. And then what's interesting is that there are cracks and voids inside of the of those energetic crystals. And then when there's a shock applied, okay, so in case of gun, when you pull the trigger, that forgot the name of this thing, but this mechanism will hit the butt of the bullet, right? And then that shock impact is going to trigger the explosion, and then that's how you fire the gun or the bullet. And the cracks and voids inside of the energetic crystals, those are the things that will collapse because of the mechanical shock. Okay. And then because of that mechanical deformation, now the energetic crystals will release some chemical energy. And then those high chemical energy is going to result in some localized heat called hotspots. So you can see that there are a bunch of hotspots. So this is a temperature field evolution. You can see a bunch of hotspot forming. And then if you have a sufficiently large number of hotspots and then they grow fast enough, then it's going to turn into a self-sustainable detonation. If there's insufficient number of hotspots and the growth rate is not above a critical threshold, then nothing is going to happen, and you'll be safe. So the funny thing, interesting thing about energetic materials is that first of all, we are interested in making those explosives safer, because during the handling or storage of energetic materials, bad things can happen. Like back in 2020 in Beirut, Lebanon, there was a big explosion. There was a storage with the ammonium nitrates, and then those are explosive materials. And then obviously during the storage, something happened. Okay, some conspiracy theorists believe that there was some spy stuck into but realistically the belief there is that during the storage the materials have developed a mechanical stress, and then because of that accumulating mechanical stress, at some point it went off, and then something bad happened. And that kind of accidents actually happens a lot, not only in military applications but also in civilian applications, because explosives and propellants are critical ingredients for mining operations, civil engineering, space missions, and a lot of things, and of course military. This is like bread and butter. And then controlling the sensitivity of these energetic materials is very important. Okay, you want the materials ideally less sensitive, but in the meantime you don't want to compromise the performance. But like in many engineering applications, if you achieve something, then you have to give up something else, right? So the sensitivity and performance, that's the trade-off that we're fighting. And then it is very well known, actually, even before my group's work, it was very well known that the sensitivity of the material is governed by not only the chemistry but also the geometric structure, okay, or the microscopic structure of the energetic crystals. So the idea was to basically optimize the microstructure of the energetic materials. Now, because we're talking about the dynamics that happens in a few nanoseconds, super fast, very violent, running this kind of simulation takes forever. Okay. So let's say, actually one of the ideas that we were working on was basically to train a generative AI, like a deepfake algorithm, to generate a fake synthetic data. Okay. So as you can see over here, this is actually a GAN generated, microstructure. So this is not real. And obviously I can control the size of the crystals. I can control the orientation of crystals, and all kind of things can be controlled. So that's great. I can generate lots of, different microstructures with varying morphology, right? And for each of those varying morphology, we run simulations. And in that way, we can find the relationship between the microstructural geometry versus material property, right? So this, by the way, can translate to pretty much every other material science problems, right? Civil engineers, work on a similar thing on porous media, right? Or, if you're in mechanical engineering, composite materials and, structural materials. I mean, you do this all the time. And then there's, a certain material property that you want to achieve, right? So, yeah, so far so good, right? So we have an ability to generate a bunch of different microstructures. We can run experiments, and in that way, we can find the relationship between the microstructure geometry versus some mechanical property. The problem is, one simulation can take about a day or two on a super. Okay, one of the best computers, by the way, in the world. It takes a day, more than a day sometimes. The reason is because, this is such a violent mechanics. We have to, have a very fine computational grid to run the simulation. And then we have to resolve the time also in a very fine grid. And the simulation takes forever. So if you're a material scientist, studying this problem, that can be really frustrating, right? You change the microstructure, and you have to wait for about a day. You come back, you get the result, and then you have to change the microstructure, run it again, and then it's going to take forever. And realistically, it's impossible. So, at the beginning, we started with this very simple formulation where the physical quantity of our interest, so X over here, is either temperature or pressure. And then we wanted to express the rate of change of temperature and pressure as a function of the current temperature and current pressure, as well as the microstructure, okay, the geometry of the input. And we simply wanted to, use the deep neural network with the model parameter theta to model that relationship. Okay. So at the beginning, we, did not think about the operator space or, Banach space or anything like that. It was a very simple formulation like this. And then, once we have this, formulation, the rate of change somehow modeled as a function f, then we should be able to integrate that over time, right? Because this function f represents time derivative. So by integrating over time for certain time interval delta t, we should be able to make a prediction of the future state of x after time delta t. Was kind of the idea. So this is our version 1 of physics-aware recurrent convolutions, or PARC. The PARC is comprised of the purple boxes and the orange boxes, or yellow boxes. Looks like. What this purple box does is to take the temperature field, a snapshot of a temperature field and a snapshot of the pressure field as an input, alongside the microstructure image as an input. So there are 3 inputs coming into the purple box: temperature, pressure, structure. And then what this purple box does is to spit out the time derivative of the temperature field and the time derivative of the pressure field. Now that, those time derivatives are then inputs to the yellow box, which then integrates the time derivatives. And then the integral of the time derivatives gets added to the previous temperature and previous pressure to make prediction of the temperature and pressure in the next time step. And we basically apply the purple box and the yellow box recursively. Okay, so the same purple box and the same yellow box are applied multiple times. And then as we apply those multiple times, we basically roll out the simulation of the temperature field and the pressure field. Was basically the idea of PARC. And as a result, we were able to predict the evolution of temperature field and the evolution of pressure field with an accuracy that was pretty okay, pretty good. All right. So the purple box over here, in terms of the terminology, we call it a differentiator CNN. And the differentiator CNN is basically, this function f over here. Now that we know all this, terminology, right? To connect this concept with neural operators, physics-informed neural net, f, or the purple box that we're learning, is basically the operator. Okay. And more precisely, it's the operator. It's a vector pointing the direction of the operator. So that by integral of that vector, okay, we're evolving the dynamics. And that's essentially how PARC works. Was there a question? Okay. So here are some more results. So these all correspond to different microstructures. So different microstructure geometry. In each panel, the animation on the left is the ground truth obtained from the numerical simulation. And then the panel on the right is the predicted result. And in terms of the location of hotspots and then their growth rate, they look pretty similar to each other. I'm not going to argue that they're exactly the same. But considering the complexity of the problem and considering the fact that the neural network prediction takes less than a second, this is a pretty decent result. Quantitatively speaking, in terms of the average temperature of the hotspots, average area of the hotspots, and their growth rate, we can see that the ground truth and the prediction is in very good agreement in general. So in this first paper, we actually compared it against other physics naive methods. So what if, for example, things like UNet or Imaginator. Imaginator, by the way, is an early days video generation algorithm. So Sora, you guys familiar with that? So the generative AI that can generate some, realistic videos. This is kind of the first generation video generation algorithm. So the idea here is that the main thesis here is that if the generative AI is so good, right? What we're generating is basically a video, and the video generation will be able to generate the video from the training data, right? Well, in fact, physics naive algorithms had some characteristics that the evolution of the temperature field was, for example, not continuous. So we would see things like, a hotspot showing up at one location, but then suddenly, transport to somewhere else, or instead the shock traveling, continuously from left to right. There were cases where the shock front show up over here, and then after time delta t goes back, and then that kind of a weird behavior. And then, like in case of the Imaginator, the shock front is not even continuous, right? So in the real world, those are the things that can never happen. Like shock wave, swipe through the space from left to right, and it never goes back and forth, or transport to some remote location, right? So the biggest thing was for UNet and Imaginator, their rate of change was kind of a discontinuous. And that, I think, is the proof that physics unaware algorithms, physics naive algorithms, even though they can mimic the visual pattern, they cannot really understand the physics, and therefore the prediction result may not be reliable, for your use case. Now, of course, the video generation algorithms nowadays are very good. Like the OpenAI Sora, for example, it can create a stunning visual with really realistic physics and everything. But that's only because, in case of the usual video generation task, there are millions of or billions of videos out there. Like there's a place called YouTube, right? The place that you spend like a few hours every day. Over there, we have like billions of videos, right? And then, you can manage to, download all those videos, use it to, train in your generative AI, and then the generative AI will learn how the human face look like, how, cats look like, because the YouTube is full of cat videos, right? And then it will learn all the relevant physics, those visual informations. Whereas, this thing over here, when we first published this paper, we had only about 30 training samples, the 30 videos. That's quite small, right? So I suspect that if there were millions of such videos, maybe the Imaginator and UNet would have done a equally good job, or maybe even better job. But under the existence of a small data, obviously those algorithms weren't able to learn the physics very well, as opposed to Park, which could capture the physics relatively well. All right, so let me, with that said, let me skip to this this figure. So we're kind of back to this figure of the space of operators and then the space of the Banach space of PDE solutions. Here we introduce one more thing, which is the tangent vector zeta. Sorry, psi. So yes, we'll get there. Short answer is it will learn any curves. Although we figured that if the dynamics is too nonlinear, then the prediction accuracy of the model is kind of quickly deteriorates. But with that caveat, there's no restriction that you have to learn only the straight line. But before we get to that discussion, here's one additional thing that we introduce, which is the idea of the tangent vector in operator. The tangent vector of an operator is essentially what generates a vector field in the Banach space. Okay, so an operator, a point on the operator space, was what generates from U0 to some corresponding point in the dynamic. The tangent vector is a mathematical function that generates the tangent vector space in the space of U. The tangent vector field, the vector field along which the dynamics can flow. Okay, so again, in case of a linear PDE, the tangent vector of the operator stays in the same direction. So the vector field is not going to change. And then in that fixed vector field, the dynamics will evolve. In case of nonlinear PDE, what's going to happen is the change in the tangent vector will induce the change in the vector field. But still, particle can flow. I'm sorry. Back. Still, a particle can flow along the vector field. Okay, similar to a particle that you drop on the Narmada River, right? The river changes its direction. The vector field, the velocity vector field of the river will change over time. It doesn't flow constantly, right? It'll change over time, and then and that leaf will follow the vector field. Every time instant, you have a different vector field. but that doesn't matter, right? Every time instance, you just vector field at the current time. And then after you follow that, the vector field change. And then you again follow the direction of the vector field. And that's going to be the trajectory of the leaf. It's the same thing. If we have a nonlinear PDE, what happens is the vector field in the U space is going to change. And then the dynamic trajectory is going to be determined by the time evolving vector field. So in theory, what Park does is to learn the tangent vectors, okay, in the operator space. And then by learning the tangent vectors, we're generating the vector field in the space of U. And then that's how we determine a unique trajectory or the solution trajectory of a partial differential equation. Okay. So this is kind of the main takeaway slide from this entire, physics aware deep learning course series. We introduced PIN, we introduced neural operator, and then now we introduced the Park. And then the evolution of the thought, okay, started from the simplest formulation, and then we develop our thoughts to include the operator space. Now we make another step. Okay, instead of considering this, now we're considering the vector field idea. And again, now that we are in the vector space, okay, we do not need to know the entire trajectory of the operator. We just need to know the steering of the vector. So that's a different thing. So again, the idea of traveling from Jabalpur to Washington, D.C., if you just know which direction you have to steer at a given moment, okay, that's easier to remember than remembering all the GPS coordinates, right, along the trajectory. And as a matter of fact, in linear PDE, you don't even have to steer. So you just need to learn one vector, and that's it. As opposed to, this is kind of the idea of learning all the GPS coordinates along the trajectory from Jabalpur to Washington, D.C. So the argument here is that this is much easier learning problem. Even though mathematically this is a lot more complicated, right? We have to, talk about the operator space. We have to talk about differential geometry, blah, blah, blah. There are a lot of things coming in. Even though the theoretical understanding of this is more difficult, at the end of the day, the learning problem itself is very simple because we just need to learn that one vector as opposed to the entire trajectory. So here's a proof. We already saw this physics-informed neural net. And then I already demonstrated that it's incredibly difficult to fit a physics-informed neural network on this, okay? Versus Park actually very quickly finds the solution. So let's wait until here. Initially, it sort of struggles, and then it picks up the vector. The moment it picks up the vector, it knows already it's some sort of oscillatory movement. And then the later, training stage is simply just adjusting that vector little by little to fine tune the frequency and fine tune the damping, coefficient. Whereas the curve fitting problem, we're still fitting the curve after 120,000 iterations, right? So, as opposed to 5,000 iterations in case of Park. Does that kind of make sense? Yeah. So, in case your dynamic trajectory is severely nonlinear. So this is an example of energetic materials, the detonation of the explosives. We have the dynamic trajectory that is visualized in the three-dimensional space. And then you can see that there are lots of kinks and then this abrupt turns. So if you treat this as a curve fitting problem, fitting a curve that looks like this is going to be very difficult. But the good news is in the operator space, this is more or less linear. Yeah, this is more or less straight line in the operator space. Although, unfortunately, I cannot visualize the operators. This is, are you familiar with the concepts like PCA? Yeah, dimensionality reduction. So it's similar to PCA. So we have some high dimensional dynamics going on, and then we reduce the dimension of that, dynamics for the visualization purpose. So we compress some high dimensional dynamics into three-dimensional space just for the sake of visualization. Yeah. So here we have a relatively smoother dynamics called the Burger's equation. And in case of Burger's equation, we have the advection term and the diffusion term, right? And the dynamics is relatively smoother. So maybe you can fit a curve nicely, but for the cases like this, it's going to be very difficult. But if you learn in the operator space, this problem becomes much simpler. So that is actually the kind of uncharted territory for this entire community, the time-dependent PDEs. So we have a pretty good confidence that, time-independent PDEs. So the difference between the time-dependent and time-independent PDEs is that the differential operator in the, differential equation, will change over time in case of the time-dependent PDEs. And then most of the problems that we're interested in the real world, the differential operator will be independent of time. So those are the time-independent PDEs. So for time-independent PDEs that are linear, we have a very strong confidence. We can solve that problem, with very, very good confidence. Time-independent nonlinear PDEs, as long as the nonlinearity is not crazy, we have a certain level of confidence that we should be able to solve that problem. Same thing with the neural operators, to be fair. But if we go to the territory of time-dependent PDEs, that's an uncharted territory. I never seen not only our group's research, but also other groups' research. I haven't seen time-dependent PDEs somehow modeled in neural networks. So that is sort of an uncharted territory that is yet to be explored. So this whole area of physics-aware deep learning is fairly new. Obviously, deep learning has only a history of just about a decade, right? And then the physics awareness is half of that history. So there's still a lot to be discovered, and unfortunately, nonlinear time-dependent PDEs, I don't think there's anybody who was able to successfully model that. So if you're, somehow considering a research career in that direction, you can work with me on that journey of, but yeah, plus I am having actually a hard time finding a practical example of, so yeah, I would say 80% of the real world applications still in the realm of time independent PDE, and then there are very few nonlinear PDE. So most of the time it's linear PDE, but yeah. But mathematically, this is a challenging thought exercise, and again, if you ever decide to go into the direction of physics over deep learning research, that is where the gold mine exists. So great question. Okay, so that's that. In case of Park, another kind of a feature that we introduced is that unlike other deep learning models, Parg is not that of a black box. Instead, you can actually visualize, certain things. And we believe that's possible because of the linearity of the learning problem. Okay, so instead of curve fitting, we're trying to find the trend, and then the trend that is learned by Parg, to a certain extent, you can visualize them. So, for example, one of the questions from the physical perspective was what contributed to the formation of hotspots, right? What are the things that contributed to the formation of hotspots? And then we introduced this technique, saliency map visualization. So this, by the way, is not our invention. In the computer vision community, there's been an attempt to visualize deep neural networks in terms of what they're doing. So saliency map technique, to oversimplify what saliency map is, it's basically the derivative. We're taking the derivative of the temperature with respect to the microstructure image. So which pixel of the microstructure has the greatest contribution to the change in temperature? Okay, is what this derivative indicates. Again, it's not exactly the evaluation of the derivative. It is a lot more sophisticated than that, but in a nutshell, we're basically evaluating that. Now, this is kind of my favorite, visualization, which is we kind of calculated that derivative and then, apply threshold. And then the ones with the high, large value of the derivative, we highlight it as red and then sort of superimpose on top of the microstructure image. First thing that we could observe is almost all times the mask was on top of a crack or pores, okay? Meaning that the hotspots are triggered by the cracks and pores. And this actually aligns with the previous understanding of what energetic materials do, like the one that I explained earlier. The pores and cracks, because of the mechanical impact, they collapse and then trigger the formation of the release of chemical energy, and that's how we create hotspots. And the fact that all the the highlighted saliency map was on that on some sort of a pore or the crack structure, sort of confirmed our previous belief. Or in other words, Parg wasn't doing something totally dumb. It was actually capturing some interesting dynamics. Now, that observation sort of led to another question, because some of the pores, some of the cracks were highlighted by the saliency map, while some other cracks were not highlighted by the saliency map. So we became curious, what's the difference, right? So actually we sampled the voids that were highlighted by Parg, and then we sampled voids that are not highlighted by the saliency map. And then we actually, listed them like this and then compared visually. And you can see that there's a, really interesting trend emerge, by displaying different voids in this manner. So for the simplicity of, discussion, we're going to call these critical voids, and then the others non-critical voids. And then there was a, pretty strong correlation tendency. Whereas, in case of the critical voids, the orientation of the voids were all lined up, left to right, whereas non-critical voids were in, any arbitrary directions, was one thing. In terms of the size of the void, they were more or less uniform, whereas non-critical voids, we had all sorts of, different sizes, from small voids to large voids. So, in fact, we measured the, the size of the void, their orientation, as well as the aspect ratio, the ratio between the skinny portion and then the length portion. We computed those morphometry and then compared the critical voids versus non-critical voids. And voila, we have the void diameter that has a statistically significant difference between critical versus non-critical, as well as the void orientation. Void orientation was the one that was most dominant. And in fact, this observation, if you present this chart to a chemist or a physicist working on an energetic material, they'll say, yeah, this makes sense, because this is kind of the empirical understanding previously, before we even presented the park and this visualization result. So it sort of confirmed the previous knowledge, but also confirmed the fact that park wasn't just weird pattern making some dumb, but it was actually making predictions based off of some physics it learned. Okay, so that's kind of the idea. So that's just the terminology. So critical doesn't mean that it's beyond some critical threshold or anything. It's just a terminology for the sake of convenience. So the way we determine critical versus non-critical, the critical voids are the ones that are highlighted by the saliency map, and the non-critical ones are the ones that are not highlighted by the saliency map. So the word critical, yeah, that may, I don't know, depending on your field, right? But it doesn't have that meaning. It's just for the, I would say, poor naming. Actually, one of the reviewers was very critical about this. We couldn't think of any better name, so. Yeah. Now, here, now that we have the park architecture defined, there are certain useful techniques that were explored by, again, my team. And this particular technique is not specific to park, but this could also be applied to neural operators and physics informed neural networks. So one of such techniques that I want to introduce is the idea of style vector in the method called style GIAN. Style GIAN is a AI. No, I think you're referring to something else. Style GIAN is a generative AI that was proposed by Karas et al. Those are the team of researchers from NVIDIA. And then they came up with this generative adversarial neural network. And then their main contribution is this idea of style vector. So style vector is, as the name indicates, it's a vector filled with lots of numbers. And those numbers are, incorporated into the, prediction process of a neural network, so that by changing the values of the style vector, you can create different, images of human faces. So like each column, for example, you have more or less the same, facial structure in terms of the location of the eyes, the composition of the overall components, but then they are in different style. The ones in the middle are white, the ones on the top are more like, people of, I think, Middle East origin. And at the bottom, we have, African, heritage there. And even for the same kind of arrangement of eyes and nose and lips, you can have different style. You can also change the hairstyle. You can change the, the skin complexion. You can change the glasses also. So this was kind of a big, important paper in the generative AI community. And the core idea of style vector is something that we borrowed, okay? And what we explored was the idea of intentionally injecting bias to the neural network prediction. And the way it works is through this adaptive input normalization layer. So in a nutshell, what happens is we compute the z-score of a neural network output, and then we scale that z-score and then shift that z-score using the learnable parameters y and ys and yb. And that is basically, ys and yb is what is determined by the style vector. So a style vector, a numerical, array that defines the style of the face comes in, and then we intentionally scale the distribution and move that distribution of the neural network output so that now we have a shifted distribution of the original prediction. And in that way, you can achieve, a different style of human faces. And we were like, aha, this is a great way of incorporating, different physical parameters and different operating conditions. So for example, here, we're defining the style vector using the operating pressure. So back to the energetic material problem, the input loading is one very important parameter that determines the thermodynamics. Obviously, if you hit it hard, then more likely it'll form lots of hot spots. If you hit it soft, then it's not gonna form a lot of hot spots. Nothing interesting is gonna happen, right? So the loading pressure is an important parameter, but this is something that is given as a scalar. So I think the question yesterday was actually, what if you have the physical parameter that is a scalar as opposed to a map, a function, right? So we wanted to tackle that exact problem. And then the idea here is to introduce the style vector and then the adaptive input normalization. So the output of the differentiator, the output of the time derivatives of the temperature and pressure, we're biasing the prediction of T dot and P dot using the pressure value. Is kind of the idea. So that when the input pressure is high, then we're biasing the T dot and P dot towards more violent reactions. So likely we're going to, exaggerate the rate of change in temperature and the rate of change in pressure. When the pressure is low, the input pressure is low, then we're biasing the T dot and P dot in the opposite direction, where we kind of intentionally suppress the rate of change in temperature and the rate of change in pressure. Now, with that training strategy, we were able to achieve this result where even for the same microstructure, we could control the evolution of the temperature field as a function of the input loading pressure. So when the pressure was 5 gigapascal, which is considered to be a weak shock, and this was the pattern of the hotspot formation. And then when the pressure loading goes up to 9.5 GPa, this was the result. And then with the 15 GPa, pretty much everything blows up. And, Park was able to model that fairly well. So far, so good? Yeah. Now, we, went a step ahead and very recently introduced this thing called the Park version 2. So if Park is about learning the tangent vector in the operator space, we wanted to further, limit our search space. So, one way to view the physics-informed neural network, neural operator in the Park is the scope of the search space. So in case of PIN, the search space was the entire Banach space. And then we went up to the neural operator where the search space is a trajectory, a single trajectory on an operator space. And then Park was the idea of learning a vector on the tangent space. So we were kind of limiting our scope of search so that the optimization problem becomes easier to solve, right? So we wanted to further reduce the search, the scope of search by introducing more, sort of a constraint into the architecture. So instead of searching for the entire vector space, where the tangent vector might be pointing at. We wanted to set a cone, okay, so that we only search within certain range of the search direction, okay? So that is the idea of Park version 2. In this case, since a lot of the problems that my group is working on, at the end of the day boils down to the advection diffusion reaction equation. So this is the generic form of the diffusion, diffusion advection reaction equation. So what we have done was to introduce the advection module, diffusion module, and the reaction module inside of the differentiator. So that instead of searching for all possible nonlinear operators, now we're searching for only the operators that has this particular form. Okay. So in that way, we're limiting our search. And since our search space is much narrower, we can converge to the optimal solution much easier. And there's a lesser risk of converging to a local minima that is not, global min. So that was the idea of Park version 2. And by introducing that, we were able to achieve a dramatic improvement. So we have the ground truth. This is another type of thermal reaction of energetic materials. Instead of the previous case where we had many, many pores, now we have a single pore, and that single pore collapses and then generates a heat like this. The Park version 1 wasn't able to capture all this detailed pattern. So Park version 1 was good at actually capturing those blurry, blobby, hotspots, but it wasn't able to capture those details. But then with Park version 2, now we are able to, capture all these vorticity patterns and, all this, advecting patterns of the hotspots. Here's another kind of, test sample. So the neural network has never seen this, microstructure during training, but yet you can see that it is able to, predict the pattern like this, which wasn't. This is kind of the value of reducing the scope. We're in the direction. The whole paddle research community is going in the direction of reducing the scope of search so that it becomes easier to train the model, right? And as a result of that, on the left-hand side, we have a Park version 1 comparison. And then on the right-hand side, we have a Park version 2 comparison. And then at this point, Park version 2 is almost accurate, almost precise compared to the ground truth. And we're actually quite both happy and scared about it. If the result is too good, then there's something wrong. But fingers crossed so far. We couldn't find any bug. So there's a good reason to believe that the Park version 2 works quite well, because even though I presented only the energetic material cases so far, we actually tested on other benchmark problems. So Berger's equation over here, we have Park version 2, which the first row is the ground truth, and then the second row is Park version 2, and Park version 2 obviously does a better job. We have Fourier neural operator. So this is something that you already know. FigCRNet, I don't know how to pronounce this, but FigCRNet is a type of physics-informed neural network. Okay, so it's a variant of a physics-informed neural network that was introduced to, incorporate varying initial conditions and varying physical parameters. And then here's a physics-informed version of Fourier neural operator. And then, none of these were able to, capture this shock front that was formed at the, bottom right corner. So you can see that the predictions are kind of blurry, whereas, both Park and Park V2 were, pretty good at making that prediction. Yes. I basically used the source code from the original authors. That's already available on the internet. Yeah. that's, I don't know, that's actually something new to, academia. Like previously, like 10, 20 years ago, everyone was hiding their code and right. And as a graduate student, I remember, sending numerous emails to authors. Can I borrow your code? I just want to test and compare my method with against yours. And then, 99% of the time you don't get any response, right? Nowadays you can just Google the name of the paper, and then, the chances you'll find a GitHub repository with the implementation. So yeah, so we were able to, make that comparison. We tweaked FNO and FCRNet for reasonable amount to make it work better. And then, the comparisons are based off of that. Here's the Navier-Stokes result. Again, free neural operator and the FCRNet, the PIN method, was able to capture the vortex shedding behind the cylinder pretty well. But like I said, they don't have a mechanism to enforce the boundary condition very well. So, you sort of see the blurry cylindrical boundary, but also in case of Fourier operator, since we're doing the low frequency, pass, right? We get to have this kind of an artifact. Again, if we increase the number of Fourier bases, then obviously this artifact will go away, but then it becomes a much difficult problem to learn because you have more bases, more coefficients to learn. Versus Park version 2, it did a pretty good job in terms of the, the phase of the oscillatory pattern, behind. This is probably the only method that was exact compared to the ground truth. And we actually got a pretty good, result like that. And then with a tougher case, now we have a compressible supersonic flow. So it's a very fast flow, and then it's compressible. So it's a lot harder, problem than the water flowing behind the cylinder. And this is the result. So the key aspects here is obviously the vortex shedding behind the cylinder, but also the formation of shock. So if you fly an hypersonic vehicle or a supersonic vehicle, beyond the speed of sound, now there's going to be what's called a bow shock that's formed in front of the of the thing. So both the formation of the bow shock and then the pattern of the oscillating vortex was pretty well captured. And again, this is the operating condition that the model has never seen during the training. So now we have an ability to, change the Mach number and then see what the reaction is going to look, the system response is going to look like. We're still working on, the geometry. So our eventual goal is to, let the model predict the flow behind different cross-sectional geometry. So that, if you're, aircraft designer, right, this can be very useful because you can change the geometry, and then each time you change the geometry, you can almost immediately predict what's going to happen, right, in different flow speed conditions. So a few more examples. Yes. We will need to train with different geometry, obviously. So we will, in the training set, training data set, imagine having, different sizes of cylinders, but also a star shape, triangle shape, square shape, geometry, right? And then, you train the model with those different geometry. And then once the training is done, we present some arbitrary geometry included in the training set. And then if the model did, right thing, to be able to predict the flow, right, around that arbitrary cross section. That's the hope. Is that going to work? Nobody knows. I guess that's still the territory that. Well, this is the boundary condition, right? So so the boundary geometry is one of the parameters to parameterize the park, right? The domain is the same, the boundary geometry changes, and then so I, so I don't know if we're speaking in the same language because I understand that different domain. I think the term boundary and things like that. There's a subtlety and nuance. So here in my lingo, we have not only the boundary defining the control volume, but also the boundary inside. And then the physical domain is the same. It's just that the boundary geometry is going to change. And the change of the boundary geometry is what we can use to parameterize park. Okay. And yeah, given that, park learn the tangent vector of the solution operator, the change in the boundary condition shouldn't, change the inherent dynamics here, right? It's just the geometry changes, but the physics principle is the same. So hopefully that operator that we learn, okay, should be generalizable to different boundary geometry. So this is kind of similar to, this situation over here. So, well, yeah, I should have, brought the microstructure geometry, but this one is also kind of like a boundary condition. So we have some four geometry that looks almost like a triangle. And then, this particular version of Park was trained on different microstructures. Boundary condition of the microstructure is going to induce a different pattern of the hotspots. So here's, yeah, this one. Yeah, we have the boundary defined like this. And then, this boundary as an input, we can make a prediction of the dynamics. So if this was possible, then there's a reason to believe that the compressible flow case, we should be able to do something similar. But that part we haven't tested yet. So still, work to be done. Yes. No, 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 no. Yeah, that so in case of pin, you will have to retrain. Neural operator and park, you don't have to. So, this one over here was trained on different microstructures, different boundaries. And this particular boundary wasn't included during the training. But without retraining park, we apply the same algorithm over here. And then we're able to predict the result that looks like this, which was pretty similar to the ground truth pattern. Um, well, things like the operating conditions, so the loading pressure might be one thing to define the direction of the dynamics, direction of the operator, right? So, like for example, the heat equation, the diffusion coefficient, is actually going to determine the length of the vector. So diffusion equation, the direction of the vector never change. So that's really, really simple, physics phenomena in that sense. But the diffusion coefficient is going to change the length of the vector. So if you have a large diffusion coefficient, the vector length is going to be, longer. So the dynamics move much faster. If you have a small diffusion coefficient, the vector is going to be shorter. Therefore, the diffusion process is going to be slower. Similarly, other physics parameters like the kinematic viscosity, for example, likely will change not only the length but also the direction, right? Yeah, so that's a question that that's a good question, but it's a question that is hard to answer because it's problem specific, right? So depending on your problem, you know, you will eventually have to use your own discretion in terms of what are the parameters that defines the physics, right? True, true. Yeah. Yeah, you're absolutely right. And that's how we, keep ourselves getting paid. Because if everything was generalizable, right, then we wouldn't need to do research, right? So problem to problem, we have different configurations, um, and it's really hard to say in one sentence that something is something. Um, so it's really problem dependent. Um, but I think if you are a domain expert, right, you would probably know what are the physical conditions that matters to you, or at least your advisor will tell you what to look for. So yeah, hopefully that answers your question. All right, other questions? The Banach space is going to stay the same. Yeah, that we're getting into the realm of time independent. Sorry, time dependent PDs, because now we have an but if there's a source term, now we have the non-homogeneous differential equation. And that I would say is an uncharted territory yet. So yeah, for that kind of a case, I don't know if any of those Park neural operator would work. Although conceptually you can still formulate, non-homogeneous cases and then train the model. But is it going to work is a different question. The neural operator, for example, if you have a control input, you can simply just have that control input as an additional input to the neural operator, right? And then let neural operator to learn what kind of role this control input plays. So in theory, you can build a neural operator, but I'm not aware of any work that has actually tested that idea. Is it going to work? There's a question mark. Same thing with Park. In theory, you can, add that as an input to Park, and then, just keep running, rolling out the prediction process. So in principle, you can do that, but is it going to work? Nobody knows. Potentially, yeah. Mm. That that's a great question, and I'll be honest, I don't have a clear answer to that. Yeah, yeah, no, I agree, and I'm happy that you guys are asking this kind of question because that is an indication that you understood the topic. Now you're up to you kind of caught up with the previous trend of research. All these questions are actually the newest questions in the research landscape. So you're I guess ready to jump on to tackle some of the newest questions in the paddle community based on the quality of your questions. So all of these questions are very interesting, and unfortunately, with that only 5 years of history of physics over deep learning, there's only there's only so much that we know, and many of those questions are actually about the things that we still don't know. So if you are curious and wants to do some work on this topic, those are exactly the directions that you may want to go. And if you figure out something, then that could be a pretty high impact paper um, with pretty strong scientific contribution. So yeah. So for graduate students sitting here, I mean, those are the research topics that could potentially be a chapter in your dissertation or whatever. And what's even better is maybe to connect that with your own experiment or with your own design problem. Um, you know what I mean? So yeah, these are all great questions. And unfortunately, I don't know the answer. I'll be honest. What else? Other questions? We're almost toward the end. Um, I don't think the tea is ready yet, so keep asking questions. Because I think I only have a few more slides. Other questions? Okay. So in summary, we have introduced Park architecture, which is comprised of the differentiator module and the integrator module. So at the implementation level, right, we simply have a recursive, architecture design where we just keep applying, differentiator and then the integrator back and forth. I mean, back to back. And then in that way, we were able to make predictions. And this is, sort of mimicking the process of how the traditional numerical solvers solve PDEs, right? Except that the differentiation and the integration is done by neural network as opposed to some numerical algorithm. We also saw that the accuracy, the prediction accuracy, and then the fidelity, the resolution of prediction was comparable to the direct numerical simulation. But in case of direct numerical simulation, some problems took hours to days on high performance computers versus Park. Most of the time, it works once it is trained. It works less than a second for the prediction. So considering that, I mean, there's a huge potential, especially like, you know, the. I mean, I show you some examples of the compressible flow and things like that. I mean, you know how long it takes to run a compressible flow simulation versus the Park prediction was about a second or less than a second on a GPU enabled computer. So my laptop, for example, has an NVIDIA GPU. It's sort of a gaming, like cheaper version of gaming laptop, and I'm able to make a prediction of the fluid pattern pretty quickly, right? So that is a great advantage of a method like Park or neural operator. And then in case of park, I think the specialty of park is when the dynamics is complicated. So to be fair, neural operators also do a great job if the dynamics is, relatively linear, which means that, the neural operator will learn the trajectory in the operator space. And then if that trajectory is not too crazy, neural operator will do a great job and might be even better than Park because neural operator is simpler than the Park implementation. So for those kind of dynamics, neural operator might be a great, option. But in case you have the dynamics that involves a lot of, violent changes, which is why, a lot of examples that I discussed today are things like the energetic materials, the detonation, or the supersonic flow, flow with the, over the speed of sound, those kind of things, where you have lots of sharp gradients, transient features, and those kind of things. Park tend to be, much better. And then the explanation here is, again, instead of learning the actual trajectory, now we're learning the vector and how to steer the vector is the difference. And then because of that, Park tend to be better than neural operators for the problems where we have sharp gradients and transient features. So with that, I'll conclude the lecture for Park. And we're going to take a break. And after the break, we'll come back and take a look at a very simplified PyTorch implementation of Park. The full implementation of Park is a lot more sophisticated. So obviously, we're going to simplify the implementation, but at least you will get the gist of what's going on, and then should be able to connect this conceptual idea with the actual implementation. So that's going to be the goal of the later part of today.